All right, so now we move into lesson 17, which is universal gravitation. Now, this lesson's all about how are two objects attracted to one another and what is that force? How do we describe it mathematically? And where are its origins in terms of how was it came about? Where were the ideas from? So, first and foremost, we start with the German mathematician and astronomer Johannes Kepler. And Johannes Kepler, what he does is he discovers or comes up with these three ways of describing planetary motion or the motion of the overall planets within any sort of solar system, namely primarily ours. And these three laws are the following. So these three laws of planetary motion, which I'll highlight here, or Kepler's three laws of planetary motion, can be described in the following way. First and foremost, the path of planets around the sun are an elliptical shape or an ellipse shape, with the center of the sun being located at one focus. This is the law of ellipse. Now, if we look at this on surface value, you're like, okay, well, I kind of know what an ellipse looks like. So, I mean, that should be straightforward enough. But when they say that the sun is at the center of one of the foci or one of the focuses, what we want to do is we're going to visualize this on another page here. So what I recommend is you have a separate piece of paper here and you draw this out. So first law, I'm just going to designate it as first law like this. What we're going to do is we're going to take a closer look at this law of ellipses, and we're going to say that, let's say I draw out the sun. So the sun is going to be right here. And let's say I draw out the ellipse that's around this. Well, the ellipse that's around this, or the path that any planetary body would take, would look something like this. Now, you're probably like, why did you draw the sun off center and not directly in the middle? Well, an ellipse has two center points or two focuses, which we call two foci. And so one of those foci is the sun itself. The other one is this small foci here, which realistically has no matter or mass in this given region, but an ellipse follows this pattern, where instead of having a one center point or one foci like a regular circle would have, a completely symmetrical circle, with an ellipse, we get these two center points or center positions. Now, if I draw this in and I annotate this, here's our sun here. Here, let's say I'm drawing the Earth's orbit. Then I'm going to make this the Earth here. Now, of course, these aren't proportional because the sun is more massive than the Earth, so we want to avoid making the sun smaller than the Earth, but just to show how this works. And then in the case of the planet going around, it's going to follow this elliptical shape here. So this is what's happening. Now, one thing to really recognize with this is we're going to talk about how the object in this ellipse, or the Earth going around the sun, or any planet that goes around the sun, has different speeds or different velocities given a different region in its ellipse. But we'll talk about that later. All we need to know that is the sun is one of these focuses or one of the foci, and then we have the Earth or whatever planet going in this ellipse shape. So this is Johannes Kepler's first law. Now, if we flip back to the second one, an imaginary area that is swept out from that center point or from that center line, from the center of the sun, I should say, outwards. And so I'm going to highlight this just using, let's say, green. An imaginary line drawn out from the center of the sun, of the planet, will sweep out equal areas in equal time intervals. And this is called the law of equal areas. Again, another one where you're like, what the heck does this mean? Now, let's actually go back to our diagram here. And what I'm going to do is I'm going to copy this exact same diagram. So if you be patient with me here, I'm just going to hold this down. Let's copy it. We'll paste it below here. There we go. And then what I'm going to annotate here is I'm going to label this as the Kepler's second law. Okay, and again, I'd recommend drawing these out because it's important to see visually how they tie to the words. Now, in the case of this one, what I'm going to do is I'm going to shift, well, I'm going to eliminate this line here because I don't want that to cause confusion about when we were talking about the motion of the object. I'm going to connect this. Now, here's what the equal areas would look like. If I draw, and I'm going to do it in the following way, from the center of the sun out to some position, let's call that position 1, and then it goes to position 2, let's say, which is over here. Well, and I'm going to even draw this skinnier here. Let's say I draw this to be position 2. Well, what I could recommend is that on the other side, if the Earth was on this other position, same but equal and opposite part of the ellipse, what we could say is that this would generate the following. I could draw a line from here to here, and then from here to here, essentially extending these out. But what I'm going to find, and I'm going to back this up just a little bit again. So I'm going to make it like this and like this. I really want to exaggerate this. So what this means is the Earth is moving from position 1 to position 2, which I'm going to call here. And this is going to be position 1 to position 2, assuming that the Earth is going this way or it's moving in the counterclockwise direction. So I'm going to write it as this: position 1 to 2, 1 to 2. According to Johannes Kepler, he said that if an equal amount of time passes, so section 1, which is going to be here, I'm going to call this section 1, if this happens in the same amount of time as this section, then the areas of these two regions should be equal. So when I write this off to the side here, if I shade this in, this is technically what the theory is saying. And then I look at this, and off to the side, I'm going to say area 1 is equal to area 2, because the time of 1 equals time of 2. So this is a really important theory. What's actually happening here? As objects are farther away from the sun, they move at a slower speed. Thus, the sliver is narrower. There's less distance traveled, but it's at a faster region, or it's at a slower region, I should say. I need to really clarify that. If you're further away from the sun, you're going to experience slower motion, but you're going to experience less overall distance covered, because obviously if it's slower, it's going to cover less distance. Therefore, in that same time interval, if you go to the other side, instead of it being really slow around here, but then being at a further distance, we're traveling very quickly over close to the object. When two objects are brought together, two objects of very large mass, or even just two objects in general, the speed is going to be a lot faster as you get brought towards the center of that larger object. So this is where the Earth is closer to the sun. It travels faster, and thus it covers more distance in that same amount of time. But when you calculate the areas, this sliver here will be equal to this sliver. And I know that's a little tough because based on the way I drew these, realistically, this one should be a little bit narrower just to really emphasize that. But we got a slower Earth speed farther away from the sun, faster speed over here. The areas are equal on one side and the other. Okay, now if that doesn't make sense, what I'm going to do is I'm going to link a video in the description, and I highly recommend you watch that just to really re-emphasize this concept and see kind of as it's happening, as it's going around this ellipse, what do those areas that get traced out look like, and that will help emphasize it. But it looks very similar to this. All right, now the last one is this one here. And this one tends to be the most confusing of them. And we go a lot more into this in lesson 18. And so just hold off on this for now in terms of like really formalizing, but it appears in the lesson 18 practice problems. The main thing you want to be is if we started with the first law that says we have these elliptical shapes or these ellipse shapes, and then what we have is this imaginary line that's drawn out from the center to the outside of the ellipse, and these areas are swept out at different intervals or same time, but just different positions in the ellipse, you're going to find that they sweep out equal areas. Last one is this one here. The ratio of the squares of the ratio of the squares of the periods of any two planets is equal to the ratio of the cubes of their average distances from the sun. So essentially what this means is that we can create these common ratios. And this is where I would highly recommend you go to that secondary video in the description, because when we talk about the law of harmonies, essentially you always get this value when you do these planetary bodies. And let's say we're comparing the sun to Earth and then the sun to Mars. Any planet that goes around the sun is roughly going to get this value of around 3.34 slash 3.35 when you calculate these ratios. And it occurs for any planet going around the sun. This relationship happens. And so that's where this word of like harmony comes around, is that we get this like kind of universal value for all planets that are going around the sun. Now, again, that one is probably the most like tricky law to really like conceptualize. There's not a ton like going into it visually. It's more about just saying, if you take any two planets within the solar system, you should get a specific thing. Okay, now to Kepler, as we scroll down here, we look at this, and I want to make a note of this. To Kepler, the planets were somehow magnetically driven to the sun's by the sun to the orbit in their elliptical trajectories. There was, however, no interaction between the planets themselves. But where we see this transition is that Kepler generates these three laws. These three laws are pretty accurate. They're good theories. They provide a good foundation for what's happening, but they don't provide the mathematical reasoning. And so what Isaac Newton does is he takes this idea that Kepler says that somehow things are magnetically driven to the sun, but then not to each other. And he's like, well, that doesn't seem right. He's troubled by this. So he says, well, I need to expand upon this and look further into this because there must be a reason that these things move in the elliptical pattern or in that elliptical shape. Now, where this happens is that there's this myth, or there's this myth story that's often told about Newton, and it's at 24, he's in an apple orchard, and then supposedly something happens where an apple comes down from the tree and strikes him in the head, and this is some sort of foundation for gravity and what gravity means. Well, we want to extend upon this, and we want to go to here, and where Newton really took this, and it's less about that apple story. The apple story is nice, and it kind of tells you a little bit about, like, hey, objects are attracted to one another. An apple falls from the tree, it's being pulled to Earth's surface. There must be sort of attractive force between the two. What Newton really does is he compares how the moon would accelerate to the Earth versus how the apple accelerates towards the Earth. And so we see these different rates of acceleration. And between these two different rates of acceleration, Newton concludes a relationship that's very powerful and helps us mathematically figure out how force is related to overall distance or radius between two centers of objects. And so when we look at this idea here, we're going to look at the following, where we say the force due to gravity, or the force, attractive force, if you want to call it that. And so I often will write this in here, just that the attractive force between two objects can be written as Fg. So Fg is the attractive force. D, which is the distance between two objects, or what I like to call the distance between two centers. And I'm going to just say the distance between the centers of objects. Now, this can also be written as the following. Fg is proportional to 1 over r squared. In fact, on your formula sheet, we use r squared instead of d squared, but the major thing we want to pull out of this is that we have this idea that Fg is proportional to 1 over the distance squared between objects, meaning it's actually inversely, the inverse squared is proportional, or Fg is proportional to the inverse square of the radius or distance between two centers of objects. And even to write this out off to the side here, what I'm going to do is just put like a circle. Whoop, I'm pulling that off to the side there. I'm going to put a circle, and then the center to center distance is, I put a center dot here, a center dot here. This would be symbolic of the r value. R value, or we can say the d value between the two of those. So from center to center, this is our radius, or the distance that we're talking about. Now, this alpha, it means proportional to. Proportional is a reflection of the change in some given value. And so if we say it's proportional to whatever the change in this 1 over r squared is, it's going to be reflected to Fg. And so we use this, it's this alpha symbol. So this is alpha. And alpha is often used in mathematics or physics in different ways. In mathematics, we often use this as like either an angle, symbolic of some sort of angle. If we're talking about trig or calculus, it's often used as a placeholder for some sort of angle. It can also be a placeholder for a lot of different variables. In physics, or primarily physics 20, we're going to use this as a value that says how are objects changing in relation to another, or what is the proportional change that is reflected by some other variable. Now, this first law here, this Fg is proportional to 1 over d squared, it is the inverse square law. It is highly recommended you highlight this in here. The mathematical relationship is the inverse square law. Now, essentially what this means is that if I have two objects, or if I have two objects that are attracted to one another, as the radius increases, the force will decrease. And as the force, or as the radius decreases, the force increases. So what I'm going to have you do is, in your notes, just to help you see this visually between here, I want you to draw in the following graph. I want you to draw this, and I want you to put Fg on the y-axis, which is the output. I want you to put radius on the x-axis. Now, what you're going to notice is that if you were to type this into your calculator, if I wanted to make this Fg is proportional to 1 over r squared, in mathematics, we can say that there is an equivalency behind 1 over r squared to 1 over x squared, where x or r are just symbolic of that radius, or just the variable we're using here. Now, if you type this into your y equals, namely, if you go y1 is equal to 1 over x squared, and you graph this, well, what you're going to notice is that when you type this in, you graph it, it's going to give you a following shape that looks like this. And I'm going to try to draw it in as accurately as possible on here. There we go. I might have to freehand it just because it's not going to be good with this. There we go. So this is roughly what the graph looks like. And so to put this verbally, what's happening is if I have a radius that's very small, well, if I trace it up to what the output is in terms of the FG is very large. So I'm going to put that over off to the side here. If I have a small radius, which I'm going to call R1, then the output or the attractive force is large between the two. If instead the radius is very large between the two, then I'm going to trace this over and I end up getting an FG that's very small with here. And this would be a radius 2 or a larger radius. And so the way I would verbally explain this, or in mathematical terms, the way I would explain this is I would say if I have a radius that is small and I get a large force, it's an exponential increase in the force or the attractive force between them. As I go and I extend my radius gets larger and larger and larger. There is an exponential decay in the force of attractiveness. That's what this 1 over x squared is. We know x squared is typically symbolic of an exponential graph, or it exponentially increases as you plug in x's. 1 over x squared in the opposite approach is saying the smaller the x, the more exponential growth there is. The larger the x is, the more exponential decay there is. And so I would just make sure to write in this in terms of in your notes, just so you can see the visual. And then when you go to a test, you could even write this in. And if they describe any sort of relationship between two objects, let's say it's like, oh, the radius doubles or the radius halves, then you can use this slider or this graph to determine, should my FG increase or should it decrease? Should the force of attractiveness increase or decrease? Okay, now here's where we continue on with Newton's ideas. And Newton develops this idea that talks about the law of gravitation extending beyond just Earth. Law of gravitation is this idea that we get the following. The law of gravitation, it can be expressed as the following. We have a force of attractiveness or an attractive force in which Fg is proportional to m1, m2 over d squared, where if I look at m1 and m2, these are a measure of the overall masses over the distance squared or the radius squared. Now, this is just a proportional statement that says I also have masses that are proportional to the Fg, or Fg that's proportional to whatever the change in mass is. The actual law of gravitation is the following. Now, this law of gravitation has a couple points that we must discuss. So what I would recommend is just highlight the universal law of gravitation, circle this equation, and then again, we're seeing this idea off to the side here of the center to center distances. What they should really do is put a center dot, arrow down, just so you see that that D, or what we call R in this unit, is that radius between the two centers, specifically when we're talking about the universal law of gravitation. Now, in this equation, or the universal gravitation equation, there's a certain element that's in this that we need to further discuss. It's this piece, the G. The G comes from, and I'm going to use a different color here, that G is the universal gravitational constant, and this came from a Cavendish experiment in which Cavendish not only found the density of the Earth, but was able to find this constant which gives us units that cancel really nicely in our gravitational equation, but then also it provides us a value that brings meaning to the mass of objects and what that means for the attractive force between two objects. And so we call this G the universal gravitational constant, and we're going to use that in calculations. Okay, now if we go over here, the last note before we start working into some problems here is going to be this one here. Note that gravitational forces are very small, even for large objects like ships, trains, etc. Gravitational force becomes very large when we talk about masses of planets or things within galaxies. So these major bodies or of mass, things that are planetary. So not just meaningless things that would be on Earth, like, a cup or, some sort of like pencil or whatever. These things are, the forces between them are going to be very, very small. When we calculate them, they would be things to like 10 to the negative 10 or 10 to the negative 12. They're just tiny forces. Whereas if we look at planets, they're going to have very large forces because they have a large amount of matter, or what we call mass. All right, now, as we go into this, before we touch on the problems, there's just a couple more notes I wanted to make within this piece here. I know I said that on the last page, but I want to really highlight the proportional statements when it comes to proportional masses and proportional 1 over r squareds, or the inverse square law and the direct proportional nature of the masses. So when we look at the universal law of gravitation, that's proposed by Newton, it states that the force of gravity acting between any two objects is directly dependent on the masses for both objects and inverse proportional to the square of the separation between the distance of the centers. Now, to further provide clarity on that, dependence on the distance, well, if we look at this here, we know that just like we said in the past, let's say I double my separation and I increase it by a factor of 2. Well, this means that the force is directly reflected by a factor of 4 or a factor of 1 over 4, and it's decreased by a factor of 4 because we know that it's going to be 1 over 4. Now, in terms of like, let's say we triple the distance between the two. Well, then we know it's going to be a factor of 9, or that it's going to be decreased by a factor of 9 because we know that if we square 3, we get 9, and so it's going to be 1 over 9. Now, where we go with this in mass and we say direct proportional in terms of mass, as I increase the mass, I'm going to expect to directly affect the overall force between the two. So in the examples here below, what they say is, let's say one of the masses is doubled, then the force of gravity between them is doubled. If one of the masses is tripled, then the force of gravity between the two should be tripled. And so mass is directly affected. And then if two masses are affected in this last line, they say if both masses are doubled, or one's tripled and one's doubled, then it's going to be the combined magnitude of those two, meaning the multiplication of those two. And we'll see what that looks like in our final example for the in-class notes today, but just be looking for that. Now, what I actually want to do is I want to make sure that I talk about the mass and the radius in terms of how they affect and what that looks like on any sort of graph. So let's see if we have some room up here. I don't think we do. So what we're going to do is, let's say I get up on another page here, just so we can represent this graphically. When we draw this, it's going to look like the following. So I want you to, again, put FG on the y-axis. I want you to put radius on the x. What we knew happened was, let's say radius, or what we do with the radius, is symbolic in red here. Well, we knew that it was inversely proportional, or the inverse square proportional, and mathematically it gave us a graph like this that either exponentially increases or exponentially decays as the radius increases or decreases. If we want to instead talk about mass, which I'm going to write in blue here, if mass is related to Fg, it's directly related. So if I change one, it affects the other. And so we would see this as mass increases, Fg increases by the exact same amount. And so if you were one of those people that's like, oh, I'd like to have little visuals that kind of like show me what my thought process should be, or how I should be associating the mass in comparison to the Fg, as the mass of objects decrease, the force of attraction decreases. As mass increases, the force of attraction increases. And so just being careful with this piece now that we have that ability to understand how mass affects it in the universal law of gravitation. Okay, now I want to flip over to here. And lastly, it's just this note that I want to make about Newton's thought process, and it's specifically about this. It's important to note that Newton's ideas describe how masses interact, but not why they interact. And so it's really important that we now have the mathematical principles, and we now have a rough mathematical understanding about how, but it's not until later on when we get Einstein in the equation, where Einstein then establishes the general theory of relativity, which is more about space-time and the overall fabric of space, which we don't really cover in this course. So where we want to really just extend upon the ideas that we've learned about today is, let's take Newton's ideas and Kepler's ideas, mash them into one, use their ideas together to then solve problems about just the general how masses interact. And then maybe down the road, let's say you go into physics 30 or beyond in terms of physics, you'll go more into this idea of relativity and how that changes our perception of how these things are interacting with one another. Okay, now let's do some practice problems. Here's what I'll give you a note on right away, and I told the classes this pretty much up front. The math in this unit is not the complex part. In fact, the only complexity around the mathematical point here is the things that I could do within the problem that might change this up a little bit. So, for example, if we are given kilograms, kilograms, and meters, that's fantastic because we know these are standardized units. Great. If we have kilograms, meters, seconds, we're in the clear. But what I could do is I could change this to grams, I could change this to like micrograms, and then I could change this to kilometers. Before you solve, you have to make sure that they're all in the standard units. So that's your heads up for this. Now, in terms of the math of this problem, like I said, it is not the troubling issue, or not the troubling part for this. So what you want to do is, as soon as they start talking about this, We have Bob and Jane, who both have mass. So these are both people on Earth, and they're sitting 1.8 meters apart. What is the gravitational force? You want to highlight that right away. Gravitational force of attraction between them. As soon as you see the mass for this piece, what you want to do is you want to write out your universal law of gravitation according to Newton. Fg, or the attractive force, is equal to G, m1, m2, divided by the radius between these two people squared, or the radius from center to center squared. Okay, now what we're going to do is we're going to write Fg, and then you're like, well, how do we know this G value? Like, we weren't given the G value. What do we know? It's actually on the back of your formula sheet. Flip your formula sheet over. It's the second one down in the constant section. It's called the universal gravitational constant. You want to use that, or more just specifically, gravitational constant. We're going to plug this in with its units. So it is 6.67 times 10 to the negative 11 newtons times meters squared divided by kilograms squared in bracket. And now we're going to put both masses. First and foremost, we're going to put 85.0, which is Bob's mass. Then we're going to put Jane's mass, which is 60.0 kilograms. And again, we're putting units with it, divided by, and then we're going to put the radius squared, 1.85 meters squared. Now, I'm going to give you a heads up. This is the number one forgot thing on test. This right here, and I'll circle it. I'll really emphasize it. The squared in the denominator. I promise there is going to be a couple of you that forget this. And the reason is because when you're doing all these things, oftentimes there's so many powers going on and there's so many different exponents in these questions that you start to see that you're like, oh, okay, well, I have this value, and then this will be the one you forget. So just really take a second before you go to your calculator. Do you have the squared right here before you move on so that you're making sure this is correct? Now, I could already tell you right away, based on the way that this problem's laid out, the force of attraction between these two, or the attractive force that appears between these two people, is going to be tiny. It's going to be very small. These are two earthly objects, and so things with a low mass relative to the general planetary body or relative to the universe, we say that this is like very low. And so in fact, when I do this in my calculator, I'm going to get an Fg, which is equal to 9.94 times 10 to the negative 8 newtons. And I'll make sure I have my negative 8 in there because I don't want to have a positive. That would mean it's a large force. Okay, that's my value. Now you're like, first and foremost, we understand the idea that the force due to gravity or the attractive force is going to be low. So that's not the hard part. Where the hard part is like, you're like, how do we end up leaving with newtons? So let's cover that right now. If I take kilograms and multiply it by kilograms, I get kilograms squared. So now I have kilograms squared here, which can cancel with kilograms squared here. Great, kilograms are gone. Now in the denominator, we have this meters squared, that goes away, and then my meters squared in the numerator goes away, therefore leaving me with the newtons here. So this is the power of the gravitational constant, is not only does it provide meaning to the masses, but it also allows us to cancel the units so we get that force that we're looking for in newtons. Now, another thing to comment on here is the reason we get a force that is more accurate, or as accurate as possible, to the overall actual attractive force between these two objects is due to this G value being so small. The G value being small helps us understand that objects with low mass relative to the whole universe should give us a low attractive force, and objects with very large masses will then be multiplied by this and scaled down, or not necessarily scaled down, but more appropriately, accurately reflected in terms of the force between them. Because if we didn't have this number here, this force of attraction would be very large, like way larger than it ever should be. And it would make us question our whole universe. This constant being in here provides meaning to things with lower mass in relation to the universe having a lower force. All right, let's try another example here. So what is the force of attraction? Again, as soon as you see that keyword, you go to your formula on your formula sheet, because this Fg equals G m1 over m2 over r squared, it's in your formula sheet. You don't have to memorize it. You don't have to guess it. Now, they say, what is the force of attraction between Mercury and the sun? See the data table below for the necessary information. So first and foremost, I'm going to write out that equation, for the equation being Fg is equal to capital G m1 m2 divided by the radius squared, or the radius between the two centers of these planets. Now, the graph that they're talking about, or the information they're talking about, is right here. And before we go on and we actually use this information, what I want to do is just indicate a couple things here. First and foremost, you're going to look at the table and be like, there's blanks right here. Why is there blanks? Well, Because the sun is the center of this given solar system. And so if it's at the center or it's the object that appears in the middle, we don't want to have any sort of mean radius orbit, because how is it going to have a radius around itself? That doesn't make sense. And then the period of revolution, well, period of revolution revolves around how long does it take to go around an object, but the sun is the object, so we shouldn't have a period of revolution. The other note I want to make is this: mean radius of orbit. What this means is, because these things are ellipses, mean, this key definition mean here, it's the average radius. And so it's very, very important we put in average radius here, implying that this thing has some sort of, because it's an ellipse, and I could even just draw this up on the top here if we really needed to. So let's say that this was the ellipse shape. Let's say that Earth is right here on the outside and it's going around. Well, it's clearly going to have all these different radiuses. It's going to have some short radiuses. It's going to have some very long radiuses. It's going to have some medium radiuses. Well, we wouldn't want to just take one of those and be like, that's the radius. So what we do is we take the infinite quantity of these, average them out, and this is that mean radius of orbit around the sun as it goes around. And I should, in my diagram, realistically, I'm going to put the sun right here, or the sun in this ellipse, because what we're thinking about is, and I'm gonna backpedal this just a little bit with my arrows, because I need to accurately reflect the theory here. So here's a large radius, because remember, it's from the center of the sun. Here's a small radius, another small radius, and then there's like a medium radius. This is what it would look like. So please don't draw that first one. This is what we're talking about, is as it's in its ellipse, we have long range or long radiuses, short radiuses, but we need that average in order to indicate what's generally happening with this object. Now, the radius of the object, this one specifically just talks about the radius of the individual planet. So please do not confuse these two. Radius around radius of orbit is around the sun. Radius of the object is just like the radius of the individual object. So please don't confuse that there. Okay, now using this information, let's actually solve the problem on the previous page. We're going to write it in the following way. So we have Fg is equal to G m1. So first and foremost, I'm going to write in my constant with units, 6.67 times 10 to the negative 11. This is newtons times meters squared divided by kilograms squared. In bracket, then we're going to write our masses in here. So first and foremost, the sun's mass is going to be, or I think I'll do Mercury's first. We get 3.28 times 10 to the 23. And this is kilograms. There we go. In brackets, we're going to write our next mass, which is the sun, 1.98 times 10 to the 30 kilograms. There we go. And then this is all divided by the radius, or the mean radius between them, which is 5.9 or 5.79. I don't want to put 79 times 10 to the, and then the power of this one is 10 to the 10 meters squared on the outside. Again, remember, this is that piece you're going to forget. I know for a fact, if you do not have this here, the value is going to be very odd. It's going to give you something that's very strange. So just take a second. Once you plug in all your numbers, you're like, okay, I've done exponent here, exponent here, exponent here, exponent here. Make sure this squared is here, because it's going to affect your value a lot if you don't have it there. Now, plugging this all into your calculator, what you're going to find is that you get the force of attraction between these two things. And if I look back at this, we're talking about planetary bodies, right? Planetary bodies have a very large attractive force to one another. So I shouldn't expect to see a low value. In fact, I should expect to see a very high value for this one. So unlike the first example, now I get 1.29 times 10 to the power of 22 newtons. Massive, massive, way larger than the two people. So the force of attraction between those two people, when we go back and compare it to that last problem, we have something that is just so much exponentially smaller than this force of attraction. Now, there's a couple notes I want you to make around this, and specifically it has to do with the force of attraction of the two people. So in that last example, before we move to the example 3, when I look at the force of attraction here, this implies that the overall acceleration between the two objects is very small. So when I get this, I'm not noticing any movement between the two people. When the two people stand next to each other and they're about a meter apart from one another, we don't claim that they're going to like all of a sudden just vacuum towards each other. That doesn't make sense. There's no sort of like overall huge force that's pushing the two together. Whereas when we look at forces between planets, there's a massive force, meaning there is a large scale acceleration or a large scale of overall motion within this problem. So just even seeing it from that lens of more traditional dynamics that we talked about at the beginning of this unit, saying, what does a force imply about two objects? And the other piece that we want to talk about here, specifically dealing with the two planetary bodies or even the two people, is that this force is an equal and opposite force. Both objects exert this force on one another. When they say force of attraction, it is a mutual force. And so that pushes us back into Newton's third law, which says, if I know that this is a force of attraction, it's a force of attraction exerted by both bodies. And so, or exerted between both bodies, if we really wanted to put it that way. All right, now going down to example 3, this one deals with proportional statements. And so I'm going to try to simplify this as much as possible, and I'm going to do the more complex way, then show a more simplified way off to the side here. So first and foremost, they say that the force between two objects is measured to be 45 newtons. And so what I'm going to do is I'm just going to write the following. Fg1, or the force due to gravity of 1, is equal to, I'm going to write G, m1, m2, divided by r squared, is equal to 45 newtons. Because they told us this original force was this, so if we were to plug these masses and the gravitational constant and the radius between them, it would give us 45. Now, where we want to transfer this is say, how does this affect the force when we play around with these numbers? So Fg2 is equal to, what is the new force if one of the masses is tripled, the other is doubled, and the distance between them is halved? Well, what I'm going to do in this equation is I'm going to do the following. G multiplied by, the first mass is tripled, the second mass is doubled, and then we have divided by, the radius ends up getting divided by 2, or I could put 1/2 in that case. So I'm just going to write it as 1/2 r with squared on the outside. And then this is going to be just as is. So we've reflected the change here. And instead of saying equals, we need to make sure that this is proportional. I'm going to start with it being proportional because it's proportional to the change in all these variables. Now, if I continue this, I'm going to get Fg is proportional to, what I'm going to do is I'm going to remove out, and I'm going to write this as Fg2 proportional. There we go. I'm going to take these and combine them together. 3 times 2 gives me 6. So I'm going to write this as 6g m1 m2. So they don't have the coefficients anymore. The coefficient was pulled out as a common factor in front of the whole thing. Now, if I distribute the 1/2 into the denominator here, well, and I should say distribute the 2 or the exponent of 2, 1/2 over 2, or 1/2 squared is equal to 1 over 4. And so if I get 1 over 4, that means that this piece becomes 1 over 4 out front, and I'm left with r squared here. Now, the one thing I want you to realize is the following. I have this numeric coefficient, and I have this piece here, which is representative of my Fg1. Because if I have nothing changed on the mass or the radius, then I know it's just the original force. Now, if I put this all together, it means that I have Fg, or Fg2, is proportional to 6 divided by 1/4 in your calculator is the same as saying 6 times 4, that's 24. That original piece there, or the part in green, is symbolic of Fg1. So therefore, my calculation is this. Fg2 is equal to 24 multiplied by that original force, which was 45.0 newtons, which then gives me a value of 1080 newtons. Or, to 3 significant digits, 1.08 times 10 to the 3 newtons, which would probably be the more correct way, I would assume, but either way in this case is fine. Now, for those of you that are like, what did we just do? Remember that if we look at this, we have some sort of original force. That original force can be represented using the original equation. Anything we change to the equation would then affect the Fg2 or create some sort of proportional statement. So that's where, when we go from equals to proportional, it's because we're describing a reflection in the change of that overall force. Once we describe the change in that force, or we say that Fg2 is proportional to this change in the original force, then we can go to that equal sign. Now, I'm going to show this in a lot more simple of a way, and you can totally replicate this on tests. I'm a-okay with you doing this. Instead, in blue, I could say Fg2 is proportional to, well, in the first case, they said it was, we multiply one of the masses by 3, the other one by 2, and the radius ends up getting halved. So it's 1/2 squared. And then this is all a reflectional change on Fg1. So I can say this change to FG1 or FG2 is proportional to this change in FG1. Now, what I'm going to do is continue this below and say FG2 is proportional to, I get that 6 divided by 1/4, just like I did before. And again, it's a reflection of the change of F1. FG2 is proportional to 24 FG1, and therefore FG2 is equal to 24 multiplied by 45.0 newtons, which then leads us back down to the exact same solution. So I know the left one might seem a little more overcomplicated, but what I always like to do is define it according to the general theory and how it would look all expanded with all the variables, or a reflection of the change on the variables, and then go from there. But honestly, if you did the stuff in blue here and you wrote it exactly how you see it there, I would be like, you know what, that is fantastic. This is great. You're showing me the theory, you're reflecting it in the appropriate way. So just know that that is equally okay. All right, here's where you're going to want to get your practice problems done. I highly recommend you do every single practice problem here. And what I would have you do is revisit the notes and go back through it. Additionally, what I want you to do is in the description of this video, I'm going to have 4 videos linked in the description for you to go and watch and learn extra on all this material, because it goes into a little bit more of Kepler's laws, Newton's ideas off of Kepler's laws, and then going even potentially into the theory of relativity. You might want to look that up on your own, but know that that's not like some requirement of Physics 20 at this point. So get the practice problems done. Like I said, the math is not going to be the difficult part, but I do want you getting experience with solving these and making sure you're putting in all the units and understanding that the difference between small masses and large masses is you get this reflection of overall force of attraction that is equal and opposite between two objects. All right, good luck with your practice.